I read the preview on this talk. I have no idea what's going on.
We'll talk about this. I was going to mention
Everyone have a seat, please. I have a couple new name tags. We have Bruce Garrett, Ken Mullen, Daniel Perez, or Tom Nedwick. Name tags. Everybody, please have a seat. I'm especially happy to introduce our speaker tonight, Dr. J.P. Sheehan. Sheehan. Sorry. Is here. His presentation is going to be called Propulsion System for CubeSATs, which are a miniature kind of spacecraft. He's going to tell you all about that. He received a PhD in nuclear engineering and nuclear physics from the University of Wisconsin-Madison 2 years ago. Currently a research fellow and lecturer at the University of Michigan, investigating the basic physics of plasma and magnetic nozzles. How's that sound? Okay. Interesting position. Okay, Dr. Sheehan.
Thank you. Whoa! Well, thanks everyone for having me here. Like Dale said, I'm going to be talking about propulsion systems for CubeSats, and specifically the CubeSat Ambipolar Thruster, which is the propulsion system that I'm working on. But before we get into all that, I'm going to back up and talk a little bit about what CubeSats are, what they can do, and what we're going to be able to make them do once we get this thruster going. So let's start out looking at a more conventional satellite, so the Hubble Space Telescope. This is one of the flagship missions that NASA and the world scientific community can produce. It's 11,000 tons. It's huge. That's an astronaut for scale. And it's really done some incredible science. I mean, no one can disagree with the images that have come back, the greater understanding of our universe that is provided, and the public relations has just been extremely powerful. It's a way to connect with the broader community and show that stuff like this, putting satellites into orbit, spending the money on it, is worthwhile. But this is extraordinarily expensive. The Hubble Space Telescope was $2.5 million and counting, which is not to say that this isn't money well spent, but showing Congress a price tag like this is becoming harder and harder to sell. Let's take another mission, Cassini, which is out at Saturn, and again, just vastly enhancing our knowledge of Saturn, of the solar system, of the beginnings of the universe. It's absolutely incredible and very, very expensive. And this is hard to sell. It's hard to get these missions to, or to get Congress to fund these missions and to keep them going for the decades that it needs to pull something like this off. So this is sort of the impetus for looking at CubeSats. Again, we have an astronaut for scale. And these are the size of the CubeSats. For instance, this is the CubeSat bus that we're using. This is one that's made by the Michigan Exploration Laboratory, which is at the University of Michigan. This is a 3-unit CubeSat. 1 unit of a CubeSat, which looks kind of like this, is a 10 centimeter by 10 centimeter by 10 centimeter cube. And you can stack these up and make larger CubeSats. So this is a 3-unit CubeSat because it's 3 of these 1 units stacked on top of each other. You can do 2U, half a U, people are talking about 6U. And the reason that these are so nice are sort of a number of different reasons. First of all, this is all standard size. So the deployer on a off-of a rocket is all standardized. You make the spacecraft to this form factor, and it can get plugged in and deployed out. You don't have to have any sort of specialty device to mount it, to launch it, that sort of thing. It's also designed to be cheap and disposable. Because these things are so small, rather than having specially designed electronics or anything like that, this is all off-the-shelf hardware. So the resistors, the integrated circuits, these are all purchased at Radio Shack and soldered onto a board. I'm absolutely not kidding.
Take your name.
And this is a really big deal because if you're putting a major satellite up into orbit, each and every component has to be X-rayed. You need to buy a batch of 10 of that component and you X-ray all of them. If there's one faulty one, you pitch it and you buy another 10. You need to know which mine the copper came from that makes the copper wires. It is such a huge production, which is part of what goes into such an expensive spacecraft. You make it small, you make it off the shelf, and you make it standardized. The price tag comes down tremendously. This price tag, the $1 million for a 3-unit CubeSat, that includes the personnel, the research, the development. The actual hardware cost for something like this is only $10,000. So very, 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 very cheap.
Is that aluminum?
This is made of aluminum. Yeah.
Can you pass it around?
Yeah, please.
Excuse me, Larry, how does the components hold up in space?
So,
I mean, especially being off the shelf stuff.
There are 2 major considerations there. One is that it's in vacuum. And one of the major ways that electronics get rid of their heat is just by conducting air. And if the electronics get too hot, they're going to melt. So that's something that can be fairly easily accounted for and tested in the lab. The other factor is radiation. You get high energy particles bombarding your electronics. Eventually there's going to be some high energy proton that hits a transistor and fries the circuit. And that's just part of the acceptance, or that's part of your accepted mission. These spacecraft typically are designed to be in orbit for a few months, 3-4 months. You could conceive of putting it into a longer-lived orbit for a year or 2, but the hardware is not going to really hold up. And frankly, the design iteration is so quick. After 3 months, you have a completely new version with higher processing, better communications, better imaging, whatever you're doing. So you want that old one to come down and launch yourself a new one to take advantage of the developments that you have. And please do interrupt. I would love to make this a discussion. Yeah.
Yeah, is there any way to shield the electronics?
There is.
Counteracting
You can. There are specific radiation shielded electronics, and the downside is that they're more expensive. And you can get most of the electronics that you would use for a CubeSat you can get in radiation hardened form. Drives the price up quite a bit. And really the idea is to keep these cheap. The great thing about these being so inexpensive is that it really breaks open satellite launching and satellite operation to a much larger community than there was before. Over 60 countries have launched CubeSats. This has become a very big thing in industry where companies are forming to launch CubeSats to do all manner of things. But it's not just restricted to NASA, JAXA, or the European Space Agency. The playing field is wide. Okay, let's think about how these things actually get up into space. Possibly out of Cape Canaveral, you have a big rocket launching, and it's carrying up some primary payload that's one of these billion-dollar satellites. Either it's a science mission that NASA's launching, or it's a company that's launching another telecommunications satellite, whatever it is. So it's getting this ride on a very, very big rocket. Inside the payload, here's your primary payload, which is whatever the large satellite is. Down here in the corner that's circled, this is what's called the P-pod, which is the deployer for the CubeSat. As you can see, it's not all that complicated. It's a box with a door and a spring. And the door opens, and it pushes the satellites out into space. It's designed to be very, very simple. There's not that much that can go wrong with this. As long as your door opens, you're on your way. And this is what's very, very important, this simplicity, because you don't want your $10,000 undergraduate-built satellite to malfunction and destroy a billion-dollar telecommunications satellite. So that's actually the main driving factor in these designs, is to protect the primary payload. If your satellite gets out, that's excellent, but you don't want to destroy the entire launch. So for instance, if you're using, if you're launching a 1U CubeSat, it'll be paired up with a couple others, and then the whole bunch of them will be stuffed into the P-pod. And for a single launch, there might be 24 CubeSats that get launched on a ride like this. There are people talking about making CubeSat-specific launches that would just, the entire payload here would just be arrays of these P-pods that could launch 1 to 200. And the rate at which CubeSat launches are growing, that is going to be the way of the future.
But wouldn't that just add to all of the other stuff that's out there with all of these little components and...
So what you bring up is space debris, and that is a very big issue, especially when you're talking about, like you said, launching high numbers of these small satellites. So there is an organization that sets guidelines for space debris. You shouldn't have a spacecraft in orbit that can stay in orbit for over 25 years. If you're going to, it needs to be moved to a disposal orbit. So for instance, the geostationary satellites are so far out there that atmospheric drag doesn't affect them at all. There's no atmosphere. They're just going to stay put. So they have propulsion systems that raise their orbit at the end of life to get them out of the way. For these small satellites, they're not going that far. The actual altitudes that they're at are typically between 250 and 900 kilometers. So the atmosphere is actually, for a spacecraft, fairly significant out there. So these will eventually deorbit if you're launched at 250 kilometers, that'll deorbit in 3 months. Like I said, there's a governing body that sort of states these guidelines, and it says that you don't want to leave stuff up there. They don't have any real authority. So if you say, too bad, I'm just put my satellite out there and leave it there, there's nothing that they can do to prevent you from doing that. But the community as a whole has accepted that this is and will continue to be a bigger and bigger issue. And so being a responsible space citizen means that you consider end of life for your satellite and how to dispose of it.
How do they keep track of each one? Is that up to whoever sends one up? How do they keep track of their own?
So there's sort of two lines to that. There is the people who are controlling the satellite, keeping track of it, and ideally you know when you've been deployed and you can sort of project where you are, aim your communications antennas to try to establish communications, and then once you've done that, you can sort of locate the satellite as it goes.
And they're going to have a lot of different tests, whatever they want to do, and that's why they're launching that.
Right. So they're launching it for some reason. Some people, because these are nice student projects, for some of them it's just ham radio relays. So you get the practice building these things, communicating with it. A lot of them are imaging the Earth, because that's sort of low-hanging fruit. Stick an iPhone camera up there and you can get some pretty decent pictures of the Earth, and pretty spectacular. Other ones are more science-based, flying through the aurora, making measurements.
That's why I was wondering what, they all have their different ideas of what they're going to do with them.
Yeah.
Now, is there, does it take a rocket that size to actually get something in orbit, or are there alternative launching methods being used?
So there are, the reason for having a launch this side is economies of scale. If you were going to launch a single one of those sorts of CubeSats, you'd still need a large enough rocket to sort of get you off the ground. By making it this size, you can launch many of them. So that's sort of the motivation. And SpaceX is really looking at the economics of this and trying to explore different solutions. But that's sort of another thing. There are alternatives to this style of launch, though. You skip ahead. You can put it on a rocket and you can send it up to the International Space Station. And there's actually a CubeSat deployer on here. So the CubeSats travel up as cargo, the astronauts load them into this deployer and launch them out.
Is that on a time basis then?
What's that?
That would be on a time basis, how long a certain one could stay there, so everybody gets, or certain people get a chance to use that particular.
That's actually run by a company. NanoRacks is the company that owned this and puts this on, and then they hired the astronauts' time. Like I said before, the small satellites, because of their low cost, you can really get a venture capital or a Series A funded company for $10 or $25 million and start doing this and making a profit. So NanoRacks has actually been extremely successful. They've launched tons and tons of these satellites. If we take a look at these two satellites in particular that they've launched here, this is two doves from Planet Labs' flock. So Planet Labs is a company that just got, some time ago, it got a Series A funding for $50 million to image the Earth. Now, the way that Earth is imaged now, there's a company called Globalstar that has these very big satellites, the typical billion-dollar size satellites, big optics that are up looking at Earth, and they sell the imaging to Google, to the CIA. There are all sorts of rules on what they can sell and to whom, but that's how Earth gets imaged right now. Planet Labs wants to do it a little bit differently. They're going to launch a number of these satellites. I think that the number is 28. And all of these are lined up in a polar orbit all together, so that as the Earth rotates and as they rotate in their orbit, they're continuously imaging the Earth. And in doing this, they think that they can get image refresh rates on the order of an image per day. So an entire image of the Earth every day. So that's what they're doing. And they want to be able to sell this to mapping, to farming, to farmers to monitor soil conditions and weather for the crops. Really, when you're doing something like that, there's all manner of very exciting things. They actually were able to photograph a forest fire in California 20 minutes after it was announced. This would be a really, really useful detection system for detecting forest fires. With a very large satellite, you really have to be choosy about where you're going to point the thing and where you're going to take pictures. So in terms of forest fires, the first detection system is I'm not even kidding about this, it's a guy in a watchtower seeing smoke. With this, you can continuously monitor. You can get better information and more accurately fight the fires. I mean, these are just, we're really just scratching the surface with the possibilities of these things. So they get deployed either off of a rocket or off of the International Space Station, and they're in some orbit. And they're there. There's no propulsion system for a CubeSat or a satellite this small. So this is what we want to do. We want to be able to design a primary propulsion system so that the CubeSat can change orbits. Maybe it needs to go in from one orbit to a different orbit. Maybe you want the CubeSat to escape Earth's influence altogether and go into deep space. There are a ton of possibilities. So we're here in Ann Arbor. This is at the University of Michigan. Here's a photo of our lab space. The lab is called PEPL, the Plasma Dynamics and Electric Propulsion Laboratory. We do lots of different electric propulsion designs. This is just the lab setup that we have for testing the CubeSat Ambipolar Thruster, or CAT. So here's a design for what CAT looks like. This aluminum frame on the outside is the one that's going around the room. In this front third or so, that'll contain all of the spacecraft controls. The computer, the battery, the pointing system, communications, everything the satellite needs to operate. That can all fit right in there. This middle third is a propellant tank. This can hold different types of propellants. The first test will use xenon, which is sort of the typical propellant used for electric propulsion systems. Xenon, or whatever the propellant is, gets fed into the plasma liner. Here we use radio frequency energy and deposit it into the gas. This ionizes it and creates a plasma. Plasmas are combinations of electrons and ions. And the cool thing about plasmas, more so than for just a hot gas, you can make use of pressure and momentum and everything that's typically found in a gas. But because it's ionized, you also get to use the electric and magnetic fields to do some really cool things. So we have electric and magnetic fields which accelerate the plasma out the back. And this actually works in a way very, very similar to a chemical rocket. In a chemical rocket, you have a chemical reaction which heats up a gas. The gas expands out through a nozzle, and the thermal energy converts into directed kinetic energy.
Now, what size is that in relation to this? Is it the same size, or is it a little larger, or is it this size?
It's the exact same size.
Oh, it is? Okay.
Yeah, because this is standard, it's standard form factor, that's the exact size that we have to work with. That's
So, how much fuel would that take? And would that be a one-time orbit change, or is it something that you can constantly, if you need to change orbit more than once? I mean, because this is such a small unit.
Yeah, depends on the mission that you want to do.
Okay.
A lot of electric propulsion is used for station keeping. So as gravitational influences pull it out of alignment, or as atmospheric drag puts it at a lower altitude, you can use the thruster to put it back where you want. For CAT, though, it's sort of its unique factor that other groups aren't really able to get out of their thrusters, is that it can provide enough change in velocity to really go someplace completely different. So most of the flights up into orbit are in some orbit around the Earth. That's not polar. It's somewhere around the equator or slightly tilted. The polar orbits are actually really interesting. There's lots of cool science that you can do if you're in a polar orbit. And with this, you can actually get there. It's a non-trivial thing to get into that orbit. It's actually a fair amount of thrust that you need to do it. So in that case, you would want a lot of propellant. You want a fairly large propellant tank. Right, so the chemical propulsion, you heat up a gas, let it expand out and generate thrust. For CAT, instead of heating up the gas particles, we ionize the gas to electrons and ions, and we just heat up the electrons. We do that. Here's an image of the plasma liner. This is made of quartz, so the plasma gets created in here. We couple the energy via an antenna, which is this. This is 3D printed out of silver. And it's actually really important. The 3D printing technology is one of the things that makes this technology possible. Afterwards, feel free to come up and take a look at it. There's a part right here which is not machinable. It can only be made by 3D printing. It's just got a weird geometry to it. The design is called a helical half twist. There are these twisting parts. The reason that we do that is that allows us to couple the radio frequency energy to a particular wave that occurs in a plasma. And that wave is really, really efficient at taking the RF electrical energy and turning it into plasma heat. So the electrons get heated up to 10 eV. We measure temperature in a unit called electron volts because 10 eV is about 100,000 degrees. So really, 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 really hot. As that plasma expands out, it follows magnetic field lines created by permanent magnets. So instead of having this big ceramic nozzle where the gas is expanding, we have no physical nozzle at all. We just have magnetic fields. And the plasma follows the magnetic field lines and expands out. The electrons lose their thermal energy, they cool down, and the ions speed up and they gain their kinetic energy. And that's basically how this thing works. Actually being able to make that happen is very tricky, but conceptually, it's the same as a chemical reactor. Everything is all encased by a Faraday shield. This is the outer part, the gray that you see here. This is also 3D printed out of titanium, and it serves two purposes. It's a Faraday shield, so it confines the radio frequency energy. That makes sure that we're putting a whole bunch of power into this part of the spacecraft. We don't want it to get into the computer or the batteries, so we want to contain it as much as possible. The Faraday shield also serves to hold all the pieces together. Magnets, antenna, plasma liner. It just comes in as a clamshell and bolts in place. And that's what you see here. On the inside are the magnets, the liner, and the antenna, which are easier to see if you come up and take a closer look afterwards. All this stuff in the back is for an old experiment that we did. The tube is to feed in the xenon. The wires are to feed in the radio frequency power. Yeah?
Do you use a standard RF frequency, like 13.56 megahertz?
We do, yeah. So,
Good question.
Just wondering the same thing.
It was not.
I know he wasn't. He was talking about it. What's the significance of that?
So 13.56 is the standard industrial frequency. Basically, the reason that we use it is because all of the experiments using on helicon devices, the basic type of device is called a helicon. All that has been done with 13.56 megahertz since 1976 when these things were discovered. It's definitely something we want to play around with because there's no reason why we use it. It's just everyone else has boilerplate.
The other thing is, if you use, that frequency and a few others are reserved for science and instrumentation kind of stuff. So if you radiate some of that frequency out through the nozzle, you're not at that frequency, you're not interfering with somebody else's protected frequency range.
And if you do go into one of those protected or those purchased frequency ranges that somebody else owns and you start broadcasting in it, the FCC is not very happy about that. That is one of the, FCC is one of the many governing bodies that we have to interact with actually putting these things in space. Yeah?
I have a question. With that 3D printing,
Yeah.
You see that titanium has, that means they have to be always in melted state? to
No,
make that
it's
thing?
laser sintered. So you use powdered titanium and then you use lasers to flash melt it and sinter it on, and it's built up like that. Yeah, that's fairly common for the metal 3D printing as opposed to plastic, which is extruded, which is the you can get 3D printers for plastic for about $1,000. They're really, really cheap. The titanium one is much more expensive.
$1 billion.
So we've got these this prototype. We have a newer one that's actually in the chamber now. And
A question.
Yeah.
So is the advantage of this plasma propulsion system over standard chemical is that you can get more power, more in a smaller unit size, and it's more efficient and all that kind of thing?
it's more efficient, you can get more thrust, and you have higher ISP, which is essentially a measurement of the fuel efficiency. Because you can get the plasma electrons heated up to 100,000 degrees, You're not, and because they're electrons, because of the magnetic fields, you're not limited by any sort of material constraints. You can have this plasma in a quartz tube, and the quartz tube won't melt. This isn't the case for chemical propulsion. If you have something that's 5,000 degrees Kelvin, you need to be putting that in a container that can be 5,000 degrees Kelvin without melting. So that's a hard limit for chemical thrusters.
So it's smaller, cheaper, faster, more efficient, etc.
That's everything.
And the fuel itself is completely benign, so it's very, it's no risk to the primary payload.
Interesting that you say that. It's the xenon itself is completely inert, not going to react with anything. We have to keep it in a pressure vessel, and the primary payload sees that as a little bomb that's kind of strapped to its side. So there are very large factors of safety, between 5 and 10, that we need for these.
And what pressures do you pressurize to?
We're really hoping to get this to 100 atmospheres. We're not sure if they'll let us fly that yet. There has not been a CubeSat yet that has flown a pressure vessel, so we're going to be blazing that red tape trail. Yes.
Question.
Yeah.
Chemical rockets, the rocket is gimbal, so you can steer it. How do you steer this?
You can steer it by pointing the spacecraft. So reaction wheels can actually point the spacecraft in the direction that you want. A reaction wheel is basically just a motor that spins a disk, and once you start spinning it one way, the spacecraft.
A gyroscope?
Yeah, essentially. Mm-hmm. So that's how we're going to do it for now.
Well, we have. But how do you so you turn the gyroscope to turn the body of the rocket, the engine?
Yeah. Yeah. So you have to turn the whole spacecraft.
Yeah.
We have what we think are some pretty cool ideas for thrust vectoring this thing, using electric and magnetic fields, but that's sort of into the future. We want to make sure that this thing just works first, and then we'll figure out how to do it. Cool stuff.
We've just been burned by the reaction wheels very noticeably in the last year. So.
Yeah, those are definitely fail. We've got our prototype, and we test this thing in a vacuum chamber. So here's an image of the plasma thruster all lit up. The propellant, the xenon, comes in from the right here, as does the power through the power lines. You can see the twist of the antenna, which is what's coupling the energy from RF electrical into the plasma. The magnets are these black bars here. These are ring-shaped magnets that produce the right magnetic field. The bright lit up part is the plasma itself. Plasma, the electrons are colliding with neutral atoms, and that's what creates the glow. Same sort of thing in the neon light, or in the fluorescent light. It's the exact same process. But what's cool about this is you can see the stream of plasma coming out of the device. And we were really, really happy to see that. The plasma follows magnetic field lines and produces this very narrow jet. This is good for efficiency because the more the jet spreads out, the more force is going sort of in this radial direction, and that helps you move your spacecraft.
Can they help figure out the lens for a second?
Yeah. Just for this image, I think. Yeah. Oh, and with the lights off, you can even see the Langmuir probe. This is the first presentation I've given where you can see the Langmuir probe. This is Langmuir probe is it's a diagnostic device for plasma. Basically, it's a bare wire that's put in the plasma. We put a voltage on it, measure current, and it's a very easy measurement to take, very difficult measurement to interpret. But this has been around. It's a device that's been around since the 1920s, so we understand a lot about this. It lets us know about the temperature, the density, the potential of the plasma, and plume. Plume is this jet that's coming out. So we're currently on a campaign to measure all the details of the plasma in the plume and make sure that we really do understand the physics of what's going on there.
What sort of thrust is this putting out?
We're expecting this to be around 1 millinewton. So a very, very, very small amount of thrust. And that's typical for electric propulsion devices. So a very low thrust, a very high fuel efficiency. So you don't have to take as much fuel along, but you need to fire for a really, really long time.
Can you relate that to something that costs how much first?
Oh, that's not going to lift. It's not going to lift the paper clip off the table. Yeah. Yeah. Even the largest thrusters that are in existence can produce a lot of a newton of thrust, and that can lift a pencil. That's about it.
But these are only going to be up there for 3 months, so that's not a long-lasting, like interplanetary probe or something like that for years.
It depends what mission you want to do. Yes, if you only want to be up there for a few months, that's fine. And that's actually for a typical electric propulsion system for on a communication satellite, something like that. They have different sorts of electric propulsion, but same sort of thrust levels. And they'll turn, if they need to reposition the satellite, they'll turn this thing on and leave it on for 2 weeks. And that'll put it back into place. Now, what we're really interested in is being able to send CubeSats to interplanetary missions. And for that, you turn this thing on, you point it where you want to go, and you let it fire for 9 months, or however long it's going to be.
What power is your radio energy on this?
10 watts. This is designed for 10 to 50 watts, which is for a CubeSat of wherever it is size. Yeah, for a CubeSat of this size, this can produce about 10 watts. Store some energy in a battery, and you can get 50 watts out of it in short bursts. If you go to a 6U, which is 2 of these side by side, now you have some more flexibility with deployable solar panels, and maybe you get to 200 watts from there. But this one in particular, we've operated it from 3 watts to 200 watts. So we've got a lot of flexibility.
Does that have the capacity to go interplanetary if you wanted to send it there, like to Mars?
So it all depends on the mission. With this thruster, we will be able to raise a 6-unit one of these from lower Earth orbit and escape Earth's gravity. Now, if we actually wanted to do an interplanetary mission, we'd get a ride up on a rocket that's already leaving, and then continue to thrust towards whatever destination. Continue to thrust towards wherever destination.
So is a slow acceleration? It eventually gets pretty fast, but starting out it's a slow acceleration.
Exactly. So the difference there is how much fuel you can take along. For instance, for small orbit adjusting maneuvers, whereas a chemical rocket or a chemical thruster might need 250 kilograms of fuel, an electric propulsion system would only need 40. And if you don't have to put that up into orbit, that makes a big difference. When you're going interplanetary, the game changes to such a degree that chemical propulsion can't get humans to Mars in a timely manner. Electric propulsion can. And that's sort of the difference. Yeah.
Is there an advantage to using other elements than xenon?
Absolutely. We are exploring iodine as a propellant. The reason that iodine is so cool and people are just starting to look at this, it stores as a solid. And you heat it up and it sublimes into a gas. And the gas has a lot of properties that are really, really similar to xenon. So we think that if we get iodine in here, then the thruster is going to perform in a similar way. So you don't have to worry about a pressure vessel. You can store more propellant because it's much, much denser. There's a little problem that it's also quite reactive. And the guys who make the solar panels don't really want to see streams of iodine eroding away all of their electrodes. But the benefits are so large that people are realizing that this is a very exciting possibility and one worth pursuing. Okay. So we're not doing this alone. Our lab are experts in electric propulsion. We do not have experience making CubeSats, which is why we're partnering with the Michigan Exploration Laboratory which is launched. They've launched 4 CubeSats in the past 5 years, and the past 2 months they've delivered 3 more. So they have some really, really good experience with this. This is one of their spacecraft. Oh, this is kind of cool. I like this a lot. These orange things that are sticking out, these are the antenna for the radio communications. This is tape measure. So tape measure. Yeah. These fold down in the pea pod, and then when it deploys, they just pop themselves out. They're good. They work really, really well. Yeah. Lots of CubeSats.
Where's that frame made at? The frame, is it?
This is made in house at the.
There's nobody manufacturing yet?
There's Pumpkin. Yeah, Pumpkin is a company that makes a CubeSat bus, and they will gladly sell you a 1-unit CubeSat for, I think they're going for about $300,000 now, somewhere in that.
How much does just the frame cost like that?
That's a very good question. This is the frame itself is Sheehan. I don't have a good answer for you because this was made by the machinists in our department that the department pays for. So we paid for the raw materials, which were like $30 or something like that for the block of aluminum. I don't have a good answer for how much this is. But they put all of this stuff together, and they know how to communicate with it, and they know how to design it. So we're using one of the existing buses.
This is U of M too?
This is also U of M, that's right. And just down the hall from us. So once it actually gets up in orbit, then we need to communicate with it. And we have a new facility that MXL has been refurbishing, which is pretty cool. It's just north of Ann Arbor. It's called Peach Mountain. It's this old satellite dish that is about 20 meters in diameter or so. They're upgrading it so that it can track the satellite. These low altitude satellites are actually moving pretty quickly across the sky. And to move a dish this big, you have to have some heavy motors on it.
85 feet.
85 feet, thank you. But this one's...
At the time it was built, it was the second largest radio telescope in the world.
Oh, wow.
Whoa. Only Jodrell Bank was larger at the time.
When was it built?
In the 50s.
So it's gone unused for a number of years. So we really want to get it back into operation. It's perfect for CubeSats. And to have our own ground station as part of the University of Michigan for this whole mission, very, very exciting. Okay, so we put our CubeSat together, or put our thruster together, put it on the CubeSat, and launch it into space. So the mission to actually test in space is the Plasma Ambipolar Thruster for responsive in-orbit transfers, or the Patriot mission. So this mission is actually a pretty big deal. The electric propulsion is one of the most difficult things, or one of the major fail points for a spacecraft. So when somebody launches one of these big missions, they are not going to risk any new technology. They're going to fly the same thing that they did last time. The same thing that they flew last time was the same thing that they flew last time. And that is the thing that was designed in 1973. And that just keeps getting flown over and over and over again. There's no room to test new technology because no one's going to risk a billion-dollar mission if they can just buy something that they know works. The great thing about the CubeSats is they're kind of designed for failure. They're designed so that you can try something, and if it doesn't work, you learn and you iterate and you try it again. So we're going to try this thruster in orbit, and our goals of the first mission are to turn it on, to see if we can actually make a plasma, communicate with it, turn the thing on and off. The secondary goal is to produce thrust and make a measurable orbit change. Learning on from that experience, we do a second iteration and actually make meaningful orbit changes, eventually getting to the point where we're leaving Earth's sphere of influence. Now, with a thruster like this that's operational and tested and can be plugged in to other people's missions, there's so many really, really cool things that you can do. The more mundane ones, like orbit changes, like I mentioned before, say that you get launched into an orbit and you can only do half of the science that you want because you're not really in an optimal place. Now you can move to the best possible orbit to do your science. You can also think about going to the Earth-Sun or Earth-Moon Lagrange points and exploring out there. Long-range, low-altitude orbits are one possibility. You just have the thruster constantly on, compensating for atmospheric drag. But the missions that I really, really want to see happen is for one rocket to go up and deploy, say, 24 of these CubeSats, have them fan out into an array and fly through the aurora for three-dimensional and temporal measurements of auroral phenomena. I mean, that's just adding,
Sign me up.
Yeah, that's adding additional dimensions of data that we just don't have right now. The science that can come out of that is just so cool. Looking ahead towards the future, I've mentioned interplanetary missions a few times. You have Europa, and we're actually designing a mission for a 6U satellite that could go to Europa. The Europa Clipper is a very large mission that NASA is planning, that NASA wants to send to explore the water geysers. The government is not keen on funding this. This is some incredibly cool and incredibly important science. Like I said before, that price tag is so large. Odds are being set at like 50-50 that it's even launched, which is a true shame because there's some incredible things that can be done. Now, if we launch a CubeSat for a few $1 million, send it out to Europa with maybe a single diagnostic to measure, to do mass spectrometry, or measure organics. Fly these through the plumes that are coming off of the geysers. Now we have a piece of hard data that we can present and say, look, hydrocarbons coming out of these geysers with water. It's important that we do a really big mission here. That sells a lot better. Getting that preliminary data with a small mission, and you could think about sending these out to many different moons, Enceladus, and really finding really interesting spots to go.
Could you have these things as like daughter craft onto
Absolutely. You think of sending a flagship.
Galileo 2 with a dozen of these things?
Yeah. Spread them out in orbit and do some incredible science. There's also also similar things are being considered just for in orbit around Earth, with the CubeSat as the mothership, and then a number of picosatellites called ChipSats, which are about yay big, being deployed. Some people are doing some cool stuff with that.
Will we be able to see that at night as the satellite going across the sky? Or is that too small?
Too small, I believe. For actually a lot of these satellites, they use ham radio. So for just the science missions, the non-commercial ones. So a lot of these you can actually track via the radio signals and listen in on what they're doing.
And that said, when I can't remember which astronaut it was, but when the tool bag was dropped, when an ISS spacewalk was going on, that was caught on film by at least a couple amateur astronomers.
Oh, is that right?
Yeah. So,
that's cool.
So at least, I don't know, I don't think it was naked eye, I think it was just an astro camera.
Yeah, I think it was just a photo.
But at least we could get pictures.
Now, if you're out by Saturn or Jupiter or something like that, can this little thing have enough power to send signals back and forth and see things?
That's one of the major challenges. There are two major challenges to get interplanetary CubeSats: propulsion system and long-distance communications. NASA is about to release a centennial challenge called the CubeSat Deep Space something or other. What they're going to do is, if you pass a number of milestones, they'll put your CubeSat on a ride that's directed towards the moon. And the goal of the challenge is to put yourself in orbit around the moon. So that requires a propulsion system that can do it, and communications that can communicate out at the moon. And then there's a prize associated with being able to accomplish those, a number of different objectives there. That's sort of the first stepping stone to getting something that can communicate.
Couldn't there be a separate mission or a parallel mission that is for establishing a communications satellite around, say, Jupiter or Mars or wherever you're going, that these two satellites could communicate with, and that communications satellite would be responsible for relaying, you know, the information back to Earth, you know, boosting the signal, et cetera, whatever you have to do. But that communication satellite is especially made for amplifying signal and just the communications part of it.
Absolutely. There's a, related to that, there's a very cool mission concept that NASA has been tossing around called the bees. I don't think there's an adjective there. I think it's just the bees. Sending up a few hundred of these things in the same orbit that Earth is, and just following Earth in a big track around the sun, using these to detect near-Earth objects, anything that's going to be coming too close to Earth. Having such a line of sight all the way around can give us more complete coverage. And then if they do detect something that's going to hit Earth, they turn into angry bees. And they can go and hit this thing, and you just crash a bunch of them into the object to readjust the orbits. So like I said, just a tremendous array of possibilities.
So if you had a sixth one, would there be like bird? Enough eggs.
Yeah, I can see that. Yeah.
If you're in orbit around a planet which has interesting hydrocarbons, like maybe Europa or Titan, it would seem like a problem would be contamination at your orbit with exhaust plumes. So how much of an advantage is contaminating your orbit with xenon, which you know is totally irrelevant to your science?
So for a CubeSat mission, getting the CubeSat into orbit around a body would be a big challenge. For most of the mission concepts would be for a rendezvous, so just a flyby, and that way you can burn up most of your xenon beforehand, and then you're not firing your thruster as you're traveling through the plumes.
I was thinking, you know, that a conventional hydrocarbon rocket would be handicapped, because you're looking for hydrocarbons and you're putting hydrocarbons into your environment.
Absolutely.
Simultaneously.
Yeah, and especially for a mission like this, for a typical deep space mission, the thrusters would be hydrazine. So you're getting hydrogen, NH, NH2, ammonia, all the things that you're looking for. But yeah, so you wouldn't get that for the xenon. Xenon's very heavy. It's atomic mass of 131 or so. So it's very distinct.
Wouldn't the solar wind blow away a certain amount of it before it could be a problem, you know, with contaminating whatever it is you're sniffing for?
So the solar wind wouldn't blow it away. Magnetic field lines of the sun and nearby bodies can redirect the exhaust. That's a process that is not very well understood, and one of the questions that we're looking into.
So what's the mass of one of these engines?
This part itself is 0.5 kilogram, which is actually pretty heavy, and it's because of the magnets on the inside. The entire system with the power unit, we're shooting for under 1 kilogram, and we think that we're going to be able to hit that.
Okay, and isn't the mass limit for the CubeSat standard 1 kilogram per U?
For a 1U, it is 1 kilogram. You can get a waiver and get up to 5 kilograms for a 3U, and that's what we're going to be shooting for. Those waivers have been quite common, so we think we manage that. I just want to mention, I do not do this alone. There's no possible way that I could. I work with Professor Longmire and Professor Cutler at the University of Michigan in the Aerospace Engineering Department. These are the 3 grad students that have been working directly on the project. And then there are also maybe 5 or 6 others that are in the lab helping out. And we have some very incredible undergraduates working with us. And really the credit is due to them. We've done amazing work. And I would love to answer more questions about this. You've been wonderful at this. I really appreciate it.
Are these CubeSats, they spotted from the Earth today, and other countries put them up there, could they be found and located?
Yeah, oh boy. I think it's the CIA tracks every object in orbit larger than a dime.
NORAD.
Yeah. Well, someone know the name of that agency?
NORAD.
NORAD, yes. So they track all of these things, and if you ask real nice, they'll tell you where your satellite is.
Often you have to tell them, especially with the small ones, and especially when they launch with a lot of other satellites. Until the orbits diverge, they don't know one object from another.
Dave, did you have a question? No. Well, what about cesium as a fuel relative to iodine?
So cesium makes a very nice plasma that was very popular in the 60s. I don't know of its being explored for propellant. It's reactive, but so is iodine. Really, we're kind of using iodine as a starting point. But cesium, definitely also a possibility. The reason that we're starting to look into this is that for the CAT thruster, it's designed so that there are no exposed metal electrodes to the plasma, as opposed to all other conventional thrusters where you have metal electrodes in the plasma. You can't use a metal propellant if they're metal electrodes because you can deposit, create a short, and ruin it. So this whole idea of these new types of propellants, widely unexplored, so cesium is definitely something that we can look at as well.
Is there anything exotic about the figuring of the magnets, or are they just straight cross sections of the cylinder?
They are exotic, and I can't tell you.
How much does the cost go up from one of the low Earth to an extended deep space mission? Is it just in the tracking and communication and duration that make it more expensive, or is it fuel or?
Duration is one of them, especially for those large missions that last for 10 years. You have personnel who are operating it that whole time.
But the CubeSat itself is pretty much the same?
CubeSat's kind of the same.
Depending on what you're trying to do?
I think because it would last for so much longer, and it's so far outside of Earth's protective magnetic field that the electronics would need to be radiation hardened. But it's so much smaller, and the launch costs are so much less that actually does make a pretty big difference. It costs, for a CubeSat this size, the going rate is $200,000 to put this into orbit. That's opposed to like a dedicated launch, which is $100 million.
How long do you think it'll take before they're used for evil?
True, shouldn't open your mouth now. You spread it to the universe.
Very novel ideas.
You mentioned using these to get astronauts to Mars faster. Can you elaborate?
Yeah, so this design is, like I mentioned, it's a type of plasma source called a helicon. This is the miniature version of this, 10 watts. You're really not going to get smaller than that. You run up against a number of physical limitations. But you can get larger, and there is a company that makes a 200 kilowatt version of this, so 20,000 times the power that this one takes. That can produce the 7 newtons of thrust. The thing's massive. It's 2.5 meters long, so 2 of these tables put together. I think it weighs in the neighborhood of 1,000 pounds or something like that. Big, beefy thing. But you can put that on some hypothetical human transport device to Mars, and you can actually get there in months. So I think that their mission design is humans to Mars in 7 months. You point it point it in the direction you want to go, and you keep firing until you get halfway there, turn the spacecraft around, you fire to slow yourself down. As opposed to a chemical rocket where you have one burn that lasts a minute, and then you're sitting for 10 years on your way.
Well, that would create kind of an artificial gravity for the crew, wouldn't it?
Not much. The thrust is so small.
Not much.
It's not quite enough. People think about how to do these things, and I think that one of the most common ones is spinning the spacecraft as you go for that.
Am I correct in recalling that the current time to get to Mars would be on the order of half a year using chemical rockets?
For a robot, yeah. For a human, it's so much more. You have to send so much more. You're limited in how much fuel you can bring up with you.
Okay, so this doesn't get them there faster exactly. It makes it possible for them to get there without getting a lethal radiation dose.
Yeah, and then there are lots. I do not know all that much about human spaceflight mission design, but there are lots of the considerations. Radiation exposure. You need to pack enough food on board the spacecraft to last 10 years. Just make your spacecraft that much bigger and that much heavier. So really, the trade-off is getting humans to Mars in a matter of months versus not going at all. That's what it is.
It's that they don't come back, right?
That's, yeah, and it's actually kind of concerning. There is, I've heard about a company that wants to put people, send people out to Mars and establish a colony. There are all sorts of ethical dilemmas with that.
That's how Australia started.
Yeah, look how that turned out.
What's Mars down here? Notice you can save a factor of 2 if you send women to Mars, because they only weigh 100 pounds.
There we go.
These things are brand new, right? I mean, how many missions have you actually, of any kind, have they've been used on?
As this thruster in particular?
Yeah, or just the CubeSats in general.
Oh, so this thruster in particular has not flown, which is, I hope I have some extra time. That's why I can show you this. There are a bunch of requirements about what you can and cannot show to people once this actually turns into a piece of flight hardware. So I'm glad that I get to show this to all of you now, because in a year I won't be able to. I'm sorry, what was the?
You know, these things are wrong.
CubeSats. CubeSats have first one launched 10 years ago, and they started out at about 5 CubeSats per year, and that's been growing exponentially. There have been, at the last count, about 250 that have been launched. This past year was a big one. With this current year that we're in, already 70 have been launched. One company launched, it just bought an entire, all the secondary spaces on a launch vehicle and launched 28 of these things. These are going to be much more common.
So these things can be piggybacked on other missions, or they can be flown up by themselves, and they're very versatile.
Very versatile.
And they're really just starting to explore the different things, different possibilities.
Right. There's a mission that just got delivered, should be launched in the fall, fingers crossed. That's putting up 8 of these, and they're all communicating with each other. So it's exploring how you, instead of just putting up a bunch of satellites and talking to each one individually, you just talk to one at a time, whichever one is most convenient, and then it relays the information to all of its buddies that are these are some of the technologies that kind of need to be developed before they become a fully functional spacecraft.
Has Amazon discussed delivering packages?
You know, it's funny you should ask.
And like that quadcopter technology.
Yeah.
Coordinated.
Well, so once PayPal Intergalactic actually gets started, there is, PayPal Galactic is a thing.
If they would have had this however many years ago, they could have avoided that iridium satellite network boondoggle.
Yeah, yeah. Yeah, that was a very expensive failure.
Well, on the other hand, with a satellite that small, you don't have much of a place to generate solar power. You're very limited in how much power you can generate on a spacecraft that small. You don't have much place to put a very high gain antennas. So
the architecture for
there are a lot of limitations.
A lot of limitations. So the architecture for a CubeSat mesh network for communications is different than that for radio. You have these low power antennas that can beam down to local ground stations. So instead of having a small receiver and a big projector, you flip it. So the receiver is much larger, and then it broadcasts locally. There's lots of interest in doing that. Facebook's big mission, one of their missions is, besides controlling every aspect of our lives, is to the internet to be linked. And this could conceivably be a way to do it.
Why a cube dimension rather than the sphere?
No particular reason. There's a competing standardization called a CubeSat, which is roughly the same size but circular cross-section.
Doesn't sound.
Exactly. Yeah. Also, this is really easy to make. That helps.
Yeah, I was going to say.
You back more.
Just a quick question.
The size was inspired by the
Is it
plastic
possible,
boxes
or is anybody considering launching it out of an airplane at high altitude?
It's funny that you should say that. Yeah, Virgin Galactic is thinking about doing that. They have a suborbital spacecraft that you can think about giving those a little bit boost. It actually, if it works, it would be much cheaper to put these things like that.
Any last questions, or we have a little bit more time tonight?
International, there are 65 different countries that have CubeSats in orbit. That's very cool. I think Ecuador, a spacefaring nation.
Peru had one launched from the International Space Station last week.
That's right. That was really cool because they didn't use nanoracks. They just had a cosmonaut hanging off the side of the space station. It was great. There's a video online. It's worth seeing. It's very cool. Yeah.
But on the other hand, it hasn't been very
Shooters who.
All right.
Has there been any scientific results from any of these missions, or are they all just kind of like proving the technology?
Well, there definitely are. MXL that we're partnering with, their first scientific mission, their second CubeSat mission was the Radial Auroral Explorer, and they flew these things through the aurora, took plasma measurements, came them back to Earth, analyzed them, all that. So there's solid science that can be done. Has been done.
They went through the maze. They went through the maze in the blue parts of the aurora.
Yeah, well, we're not going to be venturing outside.
All right, well, let's thank our speaker.
How much money?
Please feel free. It's very cool.
Gail and I were just.
Right. I'm gonna be able to take a picture of it.
Did you catch his name?
No, I'm sorry. Yeah, I appreciate that. Okay. Feel free to take pictures of the antenna, just not the.
No, it's fine.
Automotive technology. Take your basic platform. Design your whole thing just for one mission, one purpose,
Yes.
and then designing another whole,
Well, it's-
making,
yeah.
another whole.
It catches.
So make use of the,
The thing about the 3D printing is that
you know, do these different things.
change the design, send the image out, get the new one, and more tweaks. So really, really
Well, a lot
fast.
of
You can
different
prototype,
I mean,
buy,
anything that you can imagine a satellite doing, this was
no,
well, like you mentioned this example of, if you look at circularity, or something, or flux, or whatever, you know. Actually, how much life there is, how much, you know,
My wife. It's fun. It's entertaining. I enjoy it.
Oh, wow.
Our conversation there.